Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra, chapter elementary transformations, lecture number 11, in which I will prove some more theorems on equivalence of matrices. Now we prove a theorem. Theorem is every non-singular matrix is a product of elementary matrices. Now we prove this. Prove. Let A is an n by n non-singular matrix. Therefore, determinant of A not equal to 0, and we may reduce A in the normal form as follow. PAQ equal to IN, where P and Q are non-singular matrices. With P equal to E1, E2 dot ES, and Q equal to F1, F2 multiply FT, E1, E2 dot ES, F1, F2 dot FT are elementary matrices. Let this is number 1, this is number 2, this is number 3, this is number 4. Pre-multiplying. Both sides of 2 by P inverse, we get P inverse PAQ equal to P inverse multiply unit matrix IN, implies that P inverse P AQ associative law equal to P inverse multiply unit matrix is P inverse. This is unit matrix. P inverse P means unit matrix. AQ equal to P inverse implies that unit matrix multiply a matrix is that matrix P inverse. This is number 5. Post multiplying. Both sides of 5 by Q inverse, we get AQ multiply Q inverse equal to P inverse Q inverse implies that A Q inverse associative law equal to P inverse Q inverse implies that A Q inverse is unit matrix IN equal to P inverse Q inverse. A multiply unit matrix is A equal to P inverse Q inverse. This is number 6 using theory and 4. In right side of 6 we get A equal to P inverse is ES multiply multiply E2 multiply E1 inverse and Q inverse equal to F1 F2 multiply Ft whole inverse. This equal to E1 inverse multiply E2 inverse multiply ES inverse, and this is Ft inverse multiply F2 inverse multiply F1 inverse. This is number 7. Since EI and Fj are elementary matrices, I equal to 1 2 S and J equal to 1 2 T implies that EI inverse and Fj inverse are elementary matrices. Therefore, from 7 we get that the matrix A is the product of elementary matrices. Proved. Now we prove the next theorem. Next theorem is, if A be any m by n matrix of rank R, then there exists a non-singular square matrix P of order m such that PA equal to a matrix in which upper part is AR and lower part is 0 matrix, where AR is an R by n matrix of rank R and 0 matrix is the A minus R by n matrix. Now we prove this. Prove. Let A is m by n size matrix and rank of A equal to R. Therefore, we may reduce A in the normal form as follow: P A Q equal to I R 0 0 0. This is number 1. This is number 2, where P is a non-singular matrix of order M, and Q is a non-singular matrix of order N. Also, P equal to product of elementary matrices E1, E2, dot 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 ES. Q equal to product of elementary matrices F1 multiply F2 multiply Ft, where E1 E2 multiply ES F1 F2 multiply Ft are elementary matrices. Let this is number 3. This is number 4. Post multiplying both sides of 2 by Q inverse, we get P A Q multiply Q inverse equal to IR 0 matrix 0 matrix 0 matrix multiply Q inverse, implies that P A Q multiply Q inverse, this is equal to I R 0 0 0. Q inverse means F1 multiply F2 multiply dot 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 Ft inverse, implies that PA multiply, this is unit matrix Q multiply Q inverse. Since Q is non-singular, so inverse exists, and here IN, this equal to IR 0 0 0. Here Ft inverse multiply F2 inverse multiply F1 inverse, implies that here PA equal to IR 0 0 matrix Ft inverse multiply F2 inverse multiply F1 inverse. Let this is number 5. Since F1 inverse F2 inverse dot 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 Ft inverse all are elementary matrices. And they are post multiplied. So in the right side we get column transformations. Since in IR 0 0 0 m by n matrix, the last a minus r rows contain only 0 elements. So elementary column transformation cannot give any change in last a minus r rows of this matrix. In right side of 5 we see post multiplication by elementary matrices which perform elementary column transformation. And we do not get any change in the last a minus r rows of right hand side of 5. Ultimately, right hand side of 5 will take the form AR0, where AR is R by n matrix and 0 is a minus r by n matrix. Hence 5 is written as PA equal to AR0 Proved. Now we prove the next theorem. Next theorem is if A be any m by n matrix of rank R, then there exists a non-singular square matrix Q such that AQ equal to a matrix, here AR, here 0 matrix, where AR is an m by R matrix of rank R and 0 is the m by n minus R matrix. Now we prove this. Prove. Let A is an m by n matrix such that rank of A equal to R. This is number 1. Since the rank of A is R, therefore the matrix A can be reduced in the normal form as follow. Here PAQ equal to IR 0 matrix 0 matrix 0 matrix. This total matrix is of size m by n. This is number 2. Where P is a non-singular matrix of order m and Q is a non-singular matrix of order n. Also, P is the product of elementary matrices E1, E2 multiply Es, and Q be the product of elementary matrices F1 multiply F2 multiply Ft. This is number 3. This is number 4. Where E1, E2 dot 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 Es, F1, F2 dot 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 Ft are all elementary matrices. Pre-multiplying both sides of 2 by P inverse. Here we write P inverse. Here PAQ, here right side P inverse, and this matrix remains same. Here by associative law, P inverse P under bracket, here AQ, here in place of P we write ES multiply dot 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 multiply E2 multiply E1 whole inverse, and this equal to E1 inverse multiply E2 inverse multiply ES inverse, and left side PB of order M. So P inverse P will be unit matrix IM, and IM multiply AQ is AQ, and right side be same. Here E1 inverse, E2 inverse, ES inverse, all are inverse of elementary matrices. So these are elementary matrices, and these elementary matrices are pre-multiplied, means we have multiplied these before this matrix. So right side of 5 will get the row transformation. Pre-multiplication of elementary matrix gives elementary row transformation. In matrix, here IR 0 matrix, 0 matrix, 0 matrix. This is m by n size matrix. The last n minus r columns. Here up to this we have r number of columns, and after this we have n minus r columns contain only 0 elements. These columns contain only 0 elements. So no row transformation can affect the last n minus r columns. These columns will not be affected by row transformations. Hence, right hand side of 5 will take the form a matrix AR0, where AR is an m by r matrix and 0 is the m by n minus r matrix. Therefore, 5 takes the form AQ equal to left side AQ equal to right side a matrix, here AR, here 0 matrix, and proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.